All right. So let me go over some instructions for the midterm quickly. All right. Okay. So try to follow your thought process and intuition. Okay. Don't try to use formulas. They are going to break. Okay. Because the way the problems are defined are trying to use some corner cases, right? Okay. So definitely there is hard to get a formula, but sometimes it might work, right? Okay. So you need to know when it works and when it breaks. Okay. And if you have doubts, right, I think it's always very easy to start from basics. Okay. I'm going to do a bunch of basic exercises which we have done so far, right, today, so that you get understanding on how to go about it, right? Okay. So what if you think a question is wrong? Okay. You can make a private post on Piazza, right? And we'll be live for more or less for the entire duration, right? Okay. But we'll try to answer your question as soon as possible. Okay. Right. By the way, no questions are wrong, right? It just, they might seem wrong because it's just really hard. Okay. Now, so can you ask for a hint, right? Okay. We can clarify questions, okay, in a way which could be helpful for you, right? Maybe it will be just rephrasing your own question in a way that becomes easier for you to understand, right? Okay. And if that is the case, right, we will just make sure that we make it public for everyone so that they also get, may not be a hint, it just maybe just simply, let's say, some input, right? Okay. Now, sorry, yeah, homework 3 solutions, right? We'll post these today midnight, okay, right? And hopefully we'll also have those graded by midnight for you to review your homeworks. But at the very least, we'll post the solutions by midnight today for sure, okay? Um, so today's lecture, right? I think I'll just quickly cover what I realize it stopped sharing. Sorry. Oh, it's back. Can you guys see the updated version today's lecture?
Yeah.
Only the one? Okay, good. All right. So we'll go over this, right? We'll essentially quickly revisit some of the concepts, right? Okay. We'll go over the constant velocity. This was lecture 12, right? Okay. And this is where you can draw the boundary for midterm, okay, in a way. All right. Uh, we wouldn't go into more details of, I think what I realized, right, that exponent of sinusoid is really, I was hoping to derive a Bessel function based thing, but I realized that's a worse thing because it seems not the part of your previous classes, right, on FFTs, right? They didn't cover that much, okay? Or they didn't even discuss how to get an FFT for exponent of a sinusoid, okay? So I don't think that makes sense, right? We'll go do something different. But after that, I'll try to go to two-tone, go to range resolution and explain how two-tone and multi-tone differ. There is a difference in them, right? Okay, in the way you analyze them, right? Okay. Then we'll cover FMCW, right? Okay. Range and resolution, right? Again, with these 3 aspects, right? FMCW, because it's more recent, I may decide that this is why this is ordered last and we may not have time to go cover this, right? But I'll try as much as I can to cover today to review all the material we have, okay? So going back to the sinusoid series, right? Okay. So just to clarify, this is the model of the reflection after your K tau LT, right? What I mean by F K tau LT is that you have a transmitter receiver signal, right? Okay. That goes through conjugate transform, right? And then you have a high pass filter, right? You go through ADC, right? You go through the first Fourier transform. This is your H of NTS, right? Comma LT. This goes to then first FFT here. And this FFT's output is F K tau, right? Comma LT, right? And then you can do a second FFT, right? This first FFT is called as a range FFT, right? Or distance FFT, call it distance FFT, okay? The second FFT is called as Doppler FFT, okay? Right, okay? So we are looking at the output of the first FFT, right? And this first FFT has the exponent in the distance, right? D1 over C, right? Okay, plus dB into sine of this thing, right? And the same thing is measured as sync, right? Okay, this is something we just covered in the latest classes, right? The problem is what we were trying to derive in the last class, right? We are trying to derive the Fourier transform, which is h k tau, comma f naught nu over c, right? as summation of this f k tau, right? L capital T multiplied by the exponent, which is positive of k2 pi f naught. We can just say for all technical purposes, nu over c, right? 2 nu over c, right? Into LT, okay, right? So this cancels the LT component in this, right? Okay, which is the small t here, right? Okay, and essentially leaves with this, right? But the question really is, what is the Fourier transform of an exponent of a sinusoid, right? If you think about it, this is exponent minus j2 pi, okay? Let me write only the sinusoid term, right? F naught into dB over C into sine of 2 pi FBT, okay, right? So this is like an exponent, right, on top of a sinusoid, okay, right? Everyone following me, Helena? I'm just trying to write the Fourier transform of this term here, okay, this particular term here, okay, using that gives me h, okay. So the h function here, okay, of k tau comma f naught nu over c, right, and the x-axis here is Doppler frequency, okay. So I took tau value corresponding to this distance d1 here, okay, the distance corresponding to d1, okay. So this tau is corresponding to d1, right, okay. And then I'm just looking at the Doppler axis here, okay. This is Doppler axis and frequency, okay. And what I did in this example is that I chose fb equals to 1 hertz, okay, right. And now I'm trying to look at the Fourier transform. This is your capital H f not nu over c at, rather, this is your h at k tau 1 comma f naught nu, right? Here you can call this as f naught nu over c axis, okay? And what you see is that you see a Doppler at 1 hertz here. This is 1 hertz. Then you see another at 2 hertz. By the way, this is in dB scale, okay? So here there is a difference between 10 dB in the first and the second hertz, 2 hertz, right? Then you also see 3 hertz, 4 hertz, and 5 hertz, 6 hertz. Basically, you see at every single, this creates a component, okay, right? So if you guys know, right, exponent of any sinusoid is a Bessel function, okay? And I was trying to derive the Bessel function in last class, and I thought, I realized, wait, I cannot do Bessel functions in this class. It takes a class of its own, okay? Does it make sense, Elena, Keshav?
Yeah, I'm not sure what a Bessel function is. I haven't really seen that before.
Forget the Bessel function. I think just remember that this Fourier transform of this kind of sinusoid looks like a crazy, which has repetition at every multiplication of the fundamental. Okay, the fundamental was FB equals to 1 hertz. Okay, right?
Right.
So we'll see every multiplicative will have its component, right? Helena, following me? I can't hear you, Helena, if you're speaking.
Yeah, I am.
Okay, it's fine to say no, by the way, guys. Okay, this is an important concept. Eric and Dylan, I know that you guys had intuition of that this will lead to cosine and like f and 2f and 3f, right? And no alternate, right? I didn't want to like explain this in the last class just because it took a lot of time. It would take a lot of time to derive the Bessel functions. Are you guys with me on this, Eric, Dylan?
Yeah, I'm following.
Yeah, I think here, I guess, there is not much to follow. The only thing I can tell you really here is that following, okay, which I already told you, right? Is that you can look into it. I can give you the derivation of how this gets, right, as a Bessel function, right? But let's go over it maybe once again. So let's say we have a human with a velocity v which is moving and starts at distance of tau d1, right, or tau 1, right? So this will essentially compose of d naught plus nu of t, right? Okay, times 2 pi fb, sorry, am I bad? dB into sine of 2 pi fp dB fpt dh into sine of 2 pi fht, okay, right? And this is essentially how the distance will go over with the function of time, okay, right? Okay. in essence, right, if I were to draw the phase response, okay, right, this is like after I narrowed down that this is the distance, right, okay, just to clarify here, right, okay, in this picture here, once I figure out the k tau 1 here, okay, which has the actual like breathing and heart rate, right, okay, I will look at this domain, okay, here, okay, and I will plot this d is what I'm plotting here, by the way, okay. I'm still going on, right? Okay, hopefully you're following this arrow, right? So the output of first Fourier is what I plotted here, okay? And it's phase, okay? Right? With time, okay? So you can think of this as a distance if you want to, okay? Right? Or you can think of this as more phase, okay? Right? Let's say I'm plotting phase at k tau 1, right? Where very specifically I see it, right? And what I do is this, rather, sorry, my bad, sorry. Let me erase this here a little bit, sorry, my bad. So what I'm doing here is really intuitively, let's say I do the phase of k tau 1, right? And this is with, sorry, I keep messing the axis up, sorry. This is your time, sorry, okay? And this is the phase of k tau 1, okay? And what I'm doing is I'm unwrapping because phase gets unwrapped after every 0, 2 pi, 4 pi, right? Okay, I'm just plotting that phase, okay? So what you see really here is this fundamental, right, on this frequency here, or the slope here, right? Okay, this is time versus phase, guys, okay? Is that clearly one, it has a slope, okay, right? That slope of the phase, right, okay, corresponds to this term, okay, v of t, because it's increasing with time, right? This term is in the first sinusoid you see here, okay, right? And the third term here is again this slightly wiggly lines on that, okay? So everyone with me, Keshav?
Yeah. Shouldn't there be a y offset also because of the d naught?
Sure, but I think this is because phase, right? So technically you can assume that d naught or just came it down to 0, okay? So we can write this down as d naught. It doesn't matter actually, okay? If you want, I think that's a more perfect representation if you want that way. That's okay, yeah. So let's say d naught, this is phase, right? Does everyone follow what I mean by phase? This is the quantity in this exponent, guys, okay, right? Or in this exponent after taking the first Fourier, okay, right? Helena, following me here?
Yeah, I am.
Eric?
Yeah, I am. I do have a question though.
Go ahead.
It was an assumption that we had made a while ago, where we had talked about that the bin where that data is actually laying that we're taking the phase from doesn't really shift around all that much.
Right.
But if we're adding this extra velocity component of the person moving, isn't that likely going to be shifting the bin that we have to pull the phase from?
Right. I think we discussed this once before, right? It's okay. I think it will shift the bin, okay? But it doesn't matter, okay? The phase will still remain like this, okay? So even if you look at a nearby bin, right, its phase will follow the same characteristic, okay? So that is the surprising part, okay? If you have this sync, right, the nearby bins, all the 3-4 bins kind of have same phase, okay? If they are influenced by assuming only one tap, okay? And they essentially carry over this information, doesn't matter if the bin change, okay? Assuming it doesn't change by many bins, okay? Does that make sense, Eric? If you think about this phase term is constant across bins.
Okay.
And therefore it can retain the information, okay? And in tomorrow's lab, you will see actually really this being done, okay? Like tomorrow's lab will be super interesting, okay? And you'll see so much powerfulness in what we can do with FMCWs, okay? I don't know why TAs are not here, but okay. All right, going forward, okay? Right, so just want to make sure that only up to doing constant velocity models, right? Okay, is going to be the part of midterm. Okay, no more than that. Okay, no like velocity upgrading over time. VT is not a function of time. Okay, that will be only the part where until which we can limit the discussion of this midterm. Okay, and tomorrow we'll see some lab example, right? Now we'll start from going from overall, quickly revising the architecture. Oh, it seems to have stopped. Folks, remind me. Quickly keep reminding me if you see I am talking and the screen is not moving. So yeah. Now I think I'll go first. This is lecture 1/2 or something along those lines. Okay. So we have overall system, right? Distance d traveled, right? And we can have transmitter and receiver transmitting sinusoid. The channel measured h, right, is one directional, right? And we can say h square is essentially can have distance d naught, this, and essentially this. This is your distance on one sided, right? And h square leads to exponent of minus 2 pi 2 dt over lambda, right? Where this is measured at h of lambda, okay, right? I see. Now, similar to this, right? Okay, as we discussed, right? The signal has same phase at alpha plus lambda by 2, alpha plus 2 lambda by 2, and so on and so forth, right? So essentially, we need to choose a frequency so that we can kind of measure the phase in a way that it leads to meeting all our specification. In this specific case, our specification of 10 centimeter for breathing, right? Okay, is what we said that will be a good way to make sure that the phase doesn't unwrap by more than 2 pi, right? Furthermore, we need the phase accuracy so that it leads to less than 0.4 millimeter, right? And we came down to this as a single tone frequency of 1.5 centimeter because lambda is this 30 centimeter for this particular frequency at 1 gigahertz. Therefore, it will be 20 centimeter, which essentially means that lambda by 2 comes down to be 10 centimeter, and that leads to 2 pi distance movement. Okay, and the accuracy requirements are also derived here. Okay, right. Next, I think going forward, right, because we want to measure the underlying distance and whatnot, right, we can kind of connect the FFTs to the distance as well, right? So let's say we have D naught, this is FB, this is your FFT of D naught plus 2 pi FBT dB, right? Okay. This is your dB and this is your DH here, okay? Essentially, this is your FFT or Fourier transform, right, of D, right, when you have infinite response for this, right? And if you take a limited window response, 0 to T naught of this, right, you essentially get a sinc function overlapping with, sorry guys, I think this is one mistake we have made so far, right, is that this was 1 over T naught, okay? Yeah, so the first 0 occurs at 1 over T naught, okay? So now essentially, right, but it doesn't change the resolution. The resolution still stays the same, right? It was just a oversight on my end, okay? So once I have this T naught observation, if I multiply the first two, right, I would essentially get sync on top of each of these three tones, okay, right? On each of these three tones, I see these syncs here, okay, right? As you can see, right, that essentially means that now we have this. This is again still a Fourier transform version, right? A continuous, right? But there does not exist nature where we can have these continuous, right? So essentially, let's assume that we are sampling this axis, right? And we are sampling this axis, let's say at a resolution of TS equals to 1 over 60 hertz. Okay. So what would happen? What would happen is really in this axis, you will have, this is an impulse train, right? Okay. It will be separated in this axis with 1 over TS, right? Which is essentially 60 hertz. Okay. So what would happen at this 60 hertz here? At 60 hertz, you will see an aliasing, correct? Okay. What I'm going to do is I'm going to take this signal here on the top, right? Okay. And this signal here, which is the sync functions or the delta functions, and I multiply with these two. Okay. And then essentially I get this period or this sampled version of the distance d here. Okay, this is a sample version of distance d, and it leads to, which is a dtft again now. Okay, because it's discrete in time and frequency, it's still continuous. Okay, what I see is essentially I would have one repetition of this sinc functions here, these three sinc functions, after every 60 hertz. Okay, right? Every 60 hertz, I would have an aliasing. Okay. Now, but at the same time, let's notice, right? What is FP? FP is typically 0.2 hertz. Okay. Right. And FH is essentially
1 hertz.
somewhere between, yeah, 1 hertz, right? Okay. So the whole point is that next thing is resolution, right? How much is our resolution in this case, guys? Keshav?
It's 1 over TS over N.
Yes, or 1 over T naught, because T naught is just nothing but 20 seconds, which is NTS, right? Okay. So it is essentially 1 over T naught, okay, which comes out to be 0.05 hertz. Okay. Everyone with me?
Yeah.
This is the resolution. Makes sense?
Mm.
So just to revise, right? Look, total time gives you resolution, right? The sampling time gives you the range or the aliasing factor. Okay. That's the easiest way to remember these things. Okay.
Professor, can you
Sound
say
good?
that again?
And in this case, sorry.
Can you say that again?
So total time T naught, okay, leads to resolution, which is 1 over T naught. Okay, that's your resolution. Okay, right? This is your total time T naught until which you observe the process. Okay, right? Then the sampling time TS gives you 1 over TS, which is essentially your range or aliasing factor into it. Okay, that's like this golden rule, simple golden rule you can follow, right? In this case, TS was 1 over 60. Okay, and therefore the range was 60 hertz here. Okay, T naught here was 20 seconds. Okay, so therefore the resolution was 0.05 hertz. Okay, 1 over T naught. Okay, now under 0.05 hertz, right, the fourth wind will have breathing because breathing is at 0.2 hertz. Okay, that's it. Does that make sense, Keshav?
Yeah.
Elena? Eric, Dylan?
Yeah.
This is like very simple way of thinking of range and resolution. Okay,
Yeah.
just 1 over their times. Okay. Dylan on par with me. Going to lecture 3-4. Okay. Sorry, Dylan, you were saying something?
I was just saying yes.
Okay. So going forward, right? Okay. So now we are talking about the ADC sampling rate, or in general, the sampling rate of the post down conversion, right? Okay. So H lambda, let's say we have two paths. Okay. Right. One each observed at lambda 1 frequency, right? And then we are observing at lambda 2. This another thing, right? Sorry, this is lambda 2 here. Okay. I need to go correct this note as well then. Okay. Now we defined the transform, Fourier transform, right? Even on lambdas, right? Which was essentially like, hey, let's take these with a positive 2D over lambdas and sum over lambdas. Okay, here. This is taking h lambda I and summing over lambdas, right? And then creating your FT, right? And we are talking about how much resolution FT will have here, okay? So we started with a simple example for two-tone, right? Let's say we have one path in the environment, right? One reflection at 2D over C. Its Fourier transform will have h lambda over infinite frequencies, all the frequencies, okay? But let's say if you only know at two frequencies, okay, right? Now at these two frequencies, what are those known will lead to the Fourier transform of this one. This is the Fourier transform you will get, right? Now if you do multiplication of these two, right, the first and the second on the right side, okay, right? what you will get is that h lambdas at those two frequencies, okay, right? But in the time domain, that will become this convolve with this particular delta function. Delta function convolve with these two exponents, okay, right? Correct? What does that mean? That essentially leads to same exponents, okay, but shifted with some tau, okay, right? Correct? So let's understand this behavior first, okay? These two exponents, right, their amplitude looks like this, okay? And the important thing to note is that when f2 minus f1, let's say, is b, okay, right? Whenever t is 1 over 2b, okay, this is one special case, okay? When t equals to 1 over tb, this becomes pi, and this becomes 1 minus 1 becomes 0, right? So essentially this goes to 0 at this point, 1 over 2b, okay? And then same thing at minus 1 over 2b, okay? Sorry. And that essentially leads to these two on the right side, okay? Now here, right, the one important thing is that because we convolve this thing, right, with the delta function of tau at tau, right, what we will get is we'll get a tau based delta function which shifted of 1 over 2b, okay, right? And it goes to 0 at tau minus 1 over 2b and tau plus 1 over 2b, right? So in this one specific two-tone case, okay, right, what is aliasing? The aliasing here is essentially
1 over b.
1 over b, okay, right? Does it make sense to everyone? Because the next peak here appears at this point, okay, right? Eric, with me?
Yeah. Yeah.
Okay. So in this only two-tone case, okay, let me just make one point here, okay? This is something which was recently posted as a clarification, okay?
Professor, really quickly, the spacing between the lambdas is b, right?
Yeah, yeah.
Okay, okay.
Yeah, this spacing is B, okay? The one note which is slightly differs from our analysis, okay, so far. In two-tone is a degenerate case, okay, a special case, let's say, okay, where the resolution is 1 over 2b, okay, and range is 1 over b, okay, only in this two-tone case, okay, all right. Now, if you go back to multi-tone cases, which we will do now soon enough, right? So now let's extend this to multi-wavelength, okay, multi-tone, okay, and you will see that there is a difference in the number, okay, but we'll come to this, okay. So let's start with again tau, where we have this entire wavelength at all frequencies, right? Let's say we only measure at a fixed bandwidth of V from F min to F max here, okay, right? Essentially, that will mean that we multiply this in frequency domain. That leads to convolution in time domain, right? So what that means is that you see a sync pulse centered around tau because these two are getting convolved here, okay?
Professor, isn't the resolution 1 over b?
Where? Yes, this is what I'm trying to tell you. In two-tone, this is a special case, okay? So two-tone, the resolution is 1 over 2b, not 1 over b, okay? Right? So this is really an important clarification, right? I think this is where, like, yeah, I think this is slightly an oversight on our end, right? I think we didn't realize that this was the difference which people were talking about, right? And the post in Piazza has been corrected, okay? So two-tone has a different solution than to multi-tone, okay? We'll get to that and we'll come back to this. Give me 1 second, okay? So let's say if I get only bandwidth B, right, and I see samples at with sync of width here, right, okay? Very important point which Keshav just pointed is that this is 1 over B and this is minus 1 over B, okay? For any rect function of bandwidth B, right, this is what it leads to, okay, right? If anybody disagrees, I think, and have a good pointer, we are happy to look at it. I somehow believe that this point was 1 over 2B, right? And that had caused a lot of mistakes in the past, okay? Or not mistakes, but the answer on the resolution, I still gave the same because I knew that answer, right? but okay. For once, I have made a mistake by following a formula. Okay. But anyways, going back, right? Point here is that this is still 1 over b, okay? Or tau plus 1 over b and tau minus 1 over b. In comparison, previously it was tau plus 1 over 2b, okay? So I want to make sure that this point is very clearly ingrained in your thought process, okay? The 0 point is slightly different here, okay?
And why does that change
So
from two-tone to multi-tone?
I will explain that part, okay? I think it doesn't actually. Technically, it's b over n minus 1, and that will become apparent, okay? Give me 1 second, okay? So here, right, let's assume that there are n points, okay, right, at which you are measuring this, right, okay? At n frequencies you are measuring, right? So what I'm going to do is I'm going to have an impulse train, right, which has essentially delta functions on all these frequencies, okay, right? And that will lead to, and this is, look, depend upon separation. So let's say separation here in between these two wavelengths here, right, is, let's say, b over n, okay, right? So if you think about that, then this aliasing factor here, right, becomes n over b, okay, right? So it's very much dependent upon the separation, okay? So now that we understand this part, right? So technically you will think that if I have two tones, right, okay, what happens is that these two tones, what I did is I did a special interesting thing is that I put one tone on the leftmost extreme and one tone on the rightmost extreme, right? So technically I only have separation of B, okay, right? And therefore this becomes 1 over B as aliasing for n equals to 2, okay? So technically you can call it that these number of points here are n plus 1 points, okay? Assuming that they are covering in that way the bandwidth B, okay, right? Does that clarify for everyone? And therefore this is n minus 1 over B, okay? Because separation between these two is very much important, right? Okay. So technically when I make n equals to large, right, this doesn't matter. But for n equals to 2, this starts mattering, okay, right? Does that make sense, Keshav?
Yeah, that makes sense now.
Okay. So, and going forward, right, the sync width here is 1 over b, okay, right? And then this is, again, for n equals to 2, this may not hold, okay? The sync width, okay, for only n equals to 2. For anything other than that, it tends to hold, okay? So going forward with that understanding, right, okay, what we have here is that we have these n plus 1 tones on the right side, okay? Oh, sorry. So we have n plus 1 tones, right, whose essentially leads to an aliasing of n over b, as we discussed, okay, right? And this still have the same resolution though, okay, of 1 over b, okay, because something needs to be separated by 1 over b so that we can kind of get that delta function out and visible, right? Anything less than 1 over b, it will absorb into the same original sync, okay? And therefore our range and resolutions are these, okay? So this is our range, right? And this is our resolution here, okay? So as I said, right, resolution has changed now, okay? This is changed from the two-tone case where it was 1 over 2b, just one special degenerate case, okay? Does that sound good? Okay. So our goal for you is that when we give you a two-tone example, start from the basics, analyze them in the way we have shown. And when we give n-tone, right, then analyze in this way, okay, right?
So going from two-tone to multi-tone, our resolution became worse, right? We went from 1 over 2b to 1 over b.
Technically, yes, in a way. That's actually slightly surprising, but yeah, it seems that's what I think me and Kshitij and Ish believe as well today, okay? Yeah, and we'll confirm it, okay, again, just to make sure that you are like, yeah, now that you say it out loud, it seems very weird. Yeah, we will confirm and double confirm on this, okay, but this is some discrepancy here, okay. Yes, but I think, yeah, we have done very formal analysis. This doesn't seem like wrong, right? We have been like thinking it again back and back. This 1 over 2b factor is perfect actually. So we are slightly surprised ourselves as well that this is happening, right? But yes, you are correct there. Okay. So two-tone is a degenerate case. Yes, for resolution. Slightly weird. Yeah. Okay. I need to think again. Sorry. In any
Are
case,
those sync widths correct? Like, is it supposed to be 1 over b instead of 1 over 2b?
yes, we did check those things yesterday. So for this midterm, we'll just go by that. Okay, and it's pretty sure correct now. Okay. Yeah, I think, yeah, we tried it out and we'll see again if again there are some things changing. Okay. So that I think brings us to completion of two-tone in one context. We have some more thoughts we want to go over. In this, basically, we'll go over scheduling of multitones. Okay. So far, we have been thinking about what range and resolution multitones will give us, right? How do we measure impulse response at all those tones is still an interesting question, right? Okay. In that context, right? Imagine, let's say we have the same thing, right? Okay. We need to estimate H at all these wavelengths, okay? Right? Sorry, this is, yeah, as it shows, right? You need to extend and measure H lambda 1, H lambda 2, and so on and so forth, right? And then we can analyze this time series to essentially get breathing and heart rate, right? As we have discussed numerous times, right? And the idea will be essentially to take IFFT and then essentially analyze that time series, okay? Now, in order to measure and how to schedule these tones, right? One of the things we discussed last time, right, is the length of how long this wavelength H lambda 1 should be, right? Okay. And one way to do was that basically we measure H lambda 1 at one instance, H lambda 2 at then second and third, and so on and so forth, right? Okay. And what we discussed, right, is that if, however, right, we measure H lambda 1, right, okay, with a time multiplex fashion, right, it could lead to lesser resolution, right? Okay. And, or rather, if we concurrently transmitted multiple tones simultaneously, right? Okay. We wanted to get the orthogonality condition, right? And what we discussed, right, is that if your time goes from T to capital NTS, which is, let's say, 1 over 60, right? Okay. So we'll essentially analyze this, right? And what we came to is that if we integrated to enough time, which is equivalent to n times b, okay, or 1 over b, right, we'll make sure all the lambda 1s and lambda 2s are orthogonal, okay? So just to explain here, right, let's say transmitter 1 is transmitting lambda 1 and lambda 2 simultaneously, okay? You see received signal having those signals coming back concurrently, right? And the problem is that y of t here, right, consists of xt minus tau, right? And let's say if I do conjugate multiply, this is your conjugate multiply with x of t, x1 of t, by the way, okay? And you try to sum it over, right? In this case, right, the problem is that we do not only have xt consist of both f1 and f2, okay? In that case, right, what we have is this particular, okay? And we are trying to multiply with conjugate of this with f1 only, right? And what we end up getting is that this one has the right component of f1 minus tau, okay? But we also have this term, right, which can act as interference, okay? Now, in order to suppress this intertone interference, okay, I'm calling this as intertone interference because we want to only see exponent of j2 pi f1 tau, okay? Because this is essentially like measuring on single frequency f1, okay? Think of this as a conjugate of just f1, okay, right? So what we technically see here is this interference, right? And what we analyze is that this interference will go to 0. This is a constant term, by the way. Okay, the second term here on the bottom. The top term needs to be summed over up to time t so that it goes to 0, right? And what we figured out, right? The amount of time it needs to go to 0 is equivalent to any wavelength of f2 minus f1. Okay, any one wave of f2 minus f1, when we sum it over, that would lead to 0 contribution from here. Okay, right? This is showing f2 minus f1's wave. Okay, right? Now f2 minus f1, let's say, is considered of b over n, right? The separation between them is b over n. Okay, right? So we essentially need this to be n over b here. Okay, so that it achieves full orthogonality. Okay, complete orthogonality. Okay, so now this n over b, right, as such, kind of is 1 over f2 minus f1, right? Okay, and this n over b, when you summed it over, right, okay, will give you only this component of f1 minus 2 pi f1 tau. Okay, everyone with me on this orthogonality? Does it recall everyone? Eric, Puneet, Dylan?
Yeah.
Remembering, recalling all these details? Elena?
Yeah.
Good. Or you want me to slow down and cover this concept a little bit more carefully? Or you recall it enough well?
Professor, I had a quick question.
Right.
So for this one, we are essentially considering that we are transmitting all the n signals at the same time, right?
Yes.
So
Concurrently.
yeah, so our x of t is a summation of f1, f2 up to fn, right? So so after this we cover FMCW waves, which is basically like which is not simultaneous transmission, but it's like different signals or multi-tones transmission one by one by one, right?
Yes.
But right before this section, we said that it's not practical to transmit the n signals one after the other.
Actually,
So
yeah, go ahead. Go ahead. Yeah.
so what was the reasoning that we first said that it's not possible, and then later we're doing the exact same thing?
No, we are not actually. Okay. It's like we are transmitting instantaneously one frequency. What FMCW does, right, Keshav, right? It's essentially transmitting one frequency at a time concurrently. Okay. So let me explain this maybe quickly. Give me a second. Okay. So let's take an example here. Okay. Right. So with FMCW, right, what is happening, right? Let's examine it. Okay. The frequency is increasing with time. Okay. Correct. Now, at any concurrent instance of time, there is only one frequency which is operational. Okay, right? In contrast, right, when we were doing one tone at a time, or when I say that it's not practical to transmit lambda 1 and then discrete lambda 2, right, lambda 3, right? Okay, it's more to do with the fact that like it's a hardware issue. And what I mean by hardware issue really is that, so for example, right, if I were to generate frequency over time, right, in a step functions like these, okay, the problem is that each time I have to lock to this frequency and then transmit this frequency, lock to this frequency, transmit this frequency, lock to this frequency, transmit this, right? However, FMCW was a nicer and easier way to transmit it, right? Okay. Okay. So what previous analysis was trying to do, Keshav, is that or everyone is that basically, can we transmit all of them simultaneously? Okay, all the tones lambda 1 to lambda n. Okay, and still get signals going back for us, right? And the problem with just transmitting this lambda 1, lambda 2, lambda 3, lambda 4 is just the hardware cost of it. Okay, right? Okay. And the second problem is that, let's say if you just transmit lambda 1, okay, right? And if lambda 1 occurs after a subsequent amount of time, okay, right? Then I think it can interfere with original lambda 1, right? But that, I think, as you said, can also happen here. That's what your point is? Is that the idea?
Right. So I was basically thinking that it's essentially sending all of the individual tones one after the other, but you're just decreasing the period of time you're sending it in, right? So you talked about instantaneous frequency being a single tone.
Yes, yes.
But basically your only disadvantage for that point was that in the frequency domain it expands out it increases the bandwidth, so your sampling time has to then your sampling rate has to increase.
True. I think
So then this whole thing just comes out to sort of be like a semantic issue where in FMCW that the tone's duration is so short that it doesn't really affect the multiple. So the other thing that we discussed where you have slightly longer tone.
so. Not exactly, right? The key benefit of FMCW is the frequency is easier to generate in this fashion. Okay, instead of like doing a step function on the right side I showed here. Okay, hardware wise, the left side is more friendly, hardware friendly, because we have these voltage controlled oscillators, right? And therefore the left side is more hardware friendly to generate. Okay, right? Yeah, that's the core reason for it. Yeah, but multitone, the problem is that you can't suppress the interference coming from the nearby reflector, okay, in a nice and simple fashion, okay. With FMCW, that basically is what the benefit you get, okay. Does that answer most of your concern?
A little bit. Maybe we can talk more after the class so that it doesn't take away from other people's time.
Okay, all right. So that's a fair point. But the whole point is that this is like a slightly hardware not so friendly, right? Okay. And this one essentially leads to that, okay. Now going back, sorry, it stopped sharing again. Okay. Sharing screen. So going with this, right? Okay. Multi-tone interference, right? Okay. So this multi-tone interference is when you have concurrent tone transmission, okay? Right? If you don't transmit concurrent tone, right, then you won't have multi-tone interference. Now we discussed that how the interference term, sorry, is essentially also related to the LCM of these times, right? Okay. And we discussed how it creates that kind of suppression, right? And there was a question we asked, right? Non-regular spacing, non-frequency, right? Okay. So still the answer for this still remains that N over B, by the way. Okay. But that's a more, yeah, concrete, actually not N over B, but yeah. So let's go over this now, okay? So this is the architecture we have, okay? We transmit all F1 to Fn simultaneously, concurrently. They get reflected back. They also get short reflection back. The received signal is then conjugate multiplied by F1 and essentially summed over all the time to get H lambda, okay? And so on and so forth, right? So you get H lambda 1 to lambda n for this time instance, right? Then you get it for, this is your time instance, right? Then you do advanced time, right? And you get it for H lambda 1 at time t for all of these H lambda n's, okay? Right? So that's kind of, you get it for N over B, then capital N over B, and so on and so forth, these different time slots, okay? Right? Everyone with me on that? Keshav?
Yeah.
So now you can analyze this to get your essentially breathing and heart rate and so on and so forth, okay? Now the biggest problem was basically following, okay? That there was this weak, strong signal which was coming directly from the transmitter to the receiver, okay? Sorry, this is flickering a lot, okay? There is a lag. Sorry.
So at every
Yeah,
So,
go ahead.
so at every sampling time n over b or 2n over b, you basically have an edge of lambda 1, lambda 2, lambda 3, all the way up to lambda n, right?
Right. For each time instance, yes.
Yeah, right. And so then basically for the next, so you can basically combine all of these. So for different time instances and then analyze that to get the bleeding and heart rate.
Yeah. Yeah.
Okay, got it.
So this is your estimate H step, okay? By the way, in the larger scheme of things, okay? Right? Remember our estimate H philosophy and then estimate kind of the next stage of it, right? Which is to take the first FFT and then you can take the second FFT against Doppler and so on and so forth, okay? Everyone following my words here, Elena?
Yeah, I'm following.
Good. So now going back to this same example, right? The problem is that the nearby signal will be reflect and have much stronger signal, right? The signal, for example, which is coming from human, right, would be maybe at a very weak amplitude here as shown, okay? A smaller tone, right? So now this guy will eat up all of your dynamic range, the stronger guy, okay? So how do we kind of protect that, okay? Now, in order to do that, right, okay, so with multitone, there is no way we can protect it, right? We need to essentially, we will hit ADC with such high power, right? Okay, the summation is essentially like your ADC, by the way, okay, right? Or like think of this as like a ADC post filtering, right? Because ADC essentially kind of does some integration without like you knowing, right? Okay, it's like an anti-aliasing filter which you apply at the front of ADC, essentially averages everything out. Okay, so it is going to eat up into your dynamic range. The other way of doing this is that you send a short pulse, right? Okay, right, and see the reflection of that short pulse. But sending this short pulse requires very high bandwidth, and it takes a lot of power and so on and so forth, right? So now, in order to avoid these interference issues, right, we went on to the FMCW variation. Okay, now, I can make one point which probably addresses what Keshav was explaining or talking about earlier, that this N over B doesn't need to be the case in the case of FMCW, right? But that's not actually the case, okay? In the case of FMCW, right? Okay, because this essentially the first strong component, right, becomes a very nearby frequency variation, right? Okay. So let me make one note here actually, okay, for FMCW, okay. So in the world of FMCW, right, you might ask, hey, I'm not integrating for the entire time of N over B, okay, right? Okay, how am I getting these orthogonalities? So technically, right, you are integrating up to N over B, okay, right? And then you're not realizing that you're integrating over N over B. What I'm trying to say is explain, let me explain it. Okay? So let's say your time t and this is your frequency, and let's say this is your f naught and this is f naught plus b here. Okay. So you're going, let's say, from in t time, right? From you're covering f naught to f naught plus b, right? Okay, in your t time, you're covering this b bandwidth, okay, right? And if you think about it, right, once you start doing sampling, right, okay, right, okay, of this using ADC, right? So let's say your T is capital NTS, right, okay. Do you see already how you are integrating it over N over B now? You essentially integrated over time NTS, okay, right, okay, right. Now what is NTS, right? This is like your equivalent to B, right, which is t, right? So in essence, you are integrating with time, which is on the horizon of n, okay? Does that make sense, this intuitive thought process? In any case, the point I want to make is that in FMCW as well, right, you are essentially integrating over the time which you were looking for, right? And it does create some residual effects because sometimes you have these things going out of this scope. Okay, all right. Okay, then so quickly, what I want to do is now essentially talk about this FMCW. Okay, in the world of FMCW, right? Okay, let's say we have this kind of frequency response. Okay, right? We have F naught plus B. It is covered in the time slot T. Okay. Now, what happens is that the nearby reflector, right, the epsilon one, right, it comes in a very closer time frame. Okay, right? And what you really here get is essentially, let's understand this, right? All these reflections you're getting back, right? Okay, they are essentially, let's call this y-axis of frequency, y. This is, let's say, your frequency axis, right? It's essentially a function of capital K times T plus F naught, okay? This is your y-axis, okay? Right, okay? Everyone follows this term? The frequency at instantaneous frequency is given by this fraction, this factor, KTF naught, okay? Keshav, with me on this?
Yeah.
Now, what this means is that whenever you, let's say, travel delta t time, in this case, epsilon time, okay, right? You essentially accumulate delta f, or rather delta f here, or rather delta f here, right? Small, okay? So you measure this y, and that gives you correspondingly x, which is delay, okay? The amount of time of travel, okay? This is your time of travel. This is the frequency offset. So you can measure this frequency offset, right? And based on that, you can reverse calculate. So essentially what you do is you take this equation of frequency, right? Okay. You know delta f on y-axis, right? That gives you delta k delta t, okay? Right? So essentially the time of travel is nothing but the frequency offset divided by capital K, okay? Right? So now it's essentially in this vein of understanding, right? Okay, that nearby reflector which are going to be strong, which will have small delta f, right? Small frequencies, okay? And those frequencies then are essentially blocked by this frequency filter, okay? And that's how you can avoid these nearby reflections, okay? And make FMCW very scalable system, right? More specific to the point is that this equation, right, kind of gives you a nice way of getting the time of flight, accurate time of flights, okay? And this essentially, right, like kind of walk through this equation again here, right? Okay, you can get distance d, right? Okay, and we have the mathematical formulation for this, right? And in summary, this mathematical formulation leads to this expression here, okay? And that expression really is F naught tau, right, which is proportional to the start frequency. And this tau square term, because k tau square becomes very small, right, this term almost becomes invisible, okay? All right, and this we showed how it scales up to multiple kind of frequencies, okay? So that gives you roughly the idea of FMCW, okay, right? Now, we'll quickly go over the range and resolution of FMCW, okay? So in the world of FMCW, sorry, right? Okay. Let's say this is your time, capital time T, okay? This is your bandwidth B, and it starts from F naught, and this is F naught plus B, right? As we derived, right? All the potentially, once you get your received signal, right? Okay. The received signal, once it's conjugate multiplied by X star of T, right? What you get post ADC, let's say this is your sampling rate Fs, okay? Also, you have a high pass filter here, assume, okay, right? What you are left with here, right, is essentially you're taking this signal and sampling at these different points in frequency, or rather both here, okay, time, okay, right? T equals to capital NTS, right? Okay. So in this case, what we derived, right, really, okay, because we are traveling bandwidth B, or we are measuring bandwidth B, right? The resolution will be 1 over B, okay, for time of travel, okay. We derived this expression, but this is a quick way of formulating, right? Now we know that time of travel is, what is time of travel, by the way? In the case of FMCW, it's 2D over C, okay, right? And whose resolution is 1 over B, okay? So in essence, right, for distance, the resolution becomes C over 2B, okay? And this we can derive in other way as well, right? We have derived this in other way in our class notes, okay? And the way we have derived this in our class notes is that essentially we covered all the wavelengths we are covering here, right? From lambda 0 to lambda naught plus B, right? We have these many tones, right? We can go over that derivation, right? Or we can go over with some other derivation here, right? Okay. So this became the resolution of this, okay? What is the range? Range is, let's understand, 1 over B is the time of travel range, okay? Or not 1 over B, N over B rather, okay? Right? And in this case, N is capital T over TS into B, okay? This is your total time of travel, okay, by the way, okay? So this now is equivalent to 2D over C, okay? So essentially the range for D, right, okay, becomes C over 2B into T upon Ts, okay, right? Or more specific to the point, okay, this you can call as C over 2B times N, okay. So just to give you, this became the range, this became the resolution, right? Okay. So when somebody asks you to design things, right, you need to know that if two things close by in distance, right? Okay. If I tell you the minimum resolution on distance, right? Okay. Then you should compare it with this 2 C over 2B. Okay. Right. That's how you kind of get to it, right? That decides your B parameter, right? Once you know the B parameter, right? Okay, you can choose your T, right? How will you choose your capital T? Can someone tell me that? Keshav?
It depends on the slope of the chirp, right?
No. What does T depends upon, right? So let's say somebody told, let's say the system spec is following, okay? I want to measure two things which are separated in distance by, say, 10 centimeter, right? Okay. And then you need to also measure, let's say, some Doppler, okay, right? Of how much? Uh, let's say 1 kilohertz, okay, right? And you need to be able to, or D max should be, let's say, somewhere between 100 meter, okay, right? Okay. If that is the spec given, right? Then that will give you essentially the value of capital N, okay, right? Correct? Resolution time Dmax divided by Dmax is essentially capital N, right? Keshav? Make sense? Elena?
Yeah.
Sorry, this
Yeah.
seemed little slightly unwavering. Yeah. Okay. In any case, okay. So you can take these centimeter and this will give you essentially 0.1 meter, and then that will give you N equals to 1000, right? Okay. That still gives you N, right? Okay. but that doesn't tell you what T and TS should be, by the way, correct? Does it?
No.
No, right? Okay. So now let's say if you have Doppler of 1 kilohertz, right? Okay. So this is, let's say, max Doppler. And then therefore, let's say another Doppler is Doppler resolution. Okay. So the maximum Doppler I need to measure is 1 kilohertz, right? What does that mean, by the way, guys? So now let's study Doppler. Okay. So how does Doppler thing work, right? So let's say these are your chirps, right? This is your T. Every T time instance, right? You get one fk tau comma lt, right? This is your essentially post Fourier. You get one row, right, which goes from 0 to k tau max, okay, or essentially call it like the range max or the time of travel max, okay, right? Okay, which is equivalent to, what is the tau max, by the way? Tau max is n over b, okay. Okay. Any case, right? Okay. Now I get these samples at every time 0, time t, at time 2t, right? Okay. But these are the samples I get, f k tau, comma l plus 1 tau t, right? Okay. Now I take the second Fourier, right, which is corresponding to the Doppler, right, guys? Okay. Let's say this is your mt. Okay. Now what is the resolution for delay and Doppler? Sorry, for Doppler rather. Resolution is, folks, very simple technique. Can someone tell me quickly, Keshav? Helena?
1 over mt.
1 over mt, yep. Guys, just see how long the process is, right? And how often you get samples. Keshav, how often we get samples? Range is?
1 over t.
Sorry. Yeah, 1 over t, okay? Because we are getting one sample at time t instance, correct? Keshav, make sense?
Yeah.
So now, what did we say? The Doppler maximum we need to measure is 1 kilohertz, right? Okay. What that tells me is that, okay, this, right, should be at least greater than 1 kilohertz, right? Okay. What that tells me is that 1 over t should be, or t should be less than 1 over 1 kilohertz, okay, right? Which is to say that t should be less than a millisecond, okay, right? Now, once you know T, right? Okay. Now you can design for TS as well. Okay. Right. What is now TS, Keshav, in the old example? Because capital N was 1000.
So you have T is NTS, right?
Yeah.
So you just substitute the values into that.
So you get 1 microsecond. Okay. Because N is 1000. Okay.
So in general, in a practical system though, TS is usually defined as your ADC sample rate. That's more of like a driving factor.
Yeah. Sorry, was that your question?
Instead of like working to TS, usually TS is like a parameter that you start with from the beginning.
No, I think you almost always start working from the system specification and go back to the ADC and other specification, right? You cannot start from ADC because you should start from application layer specification, okay? Does that make sense?
Yeah, that makes sense.
So I have maybe a challenging question given like in the last 5 minutes, right? Okay. So tell me how many bits of ADCs I should design it for. So far, like guys, we have been looking at range, okay, resolution, okay, What is the third thing we have to do almost always? Accuracy. Okay. So we have been talking about range resolution accuracy in the early on when we were discussing this class. We were talking a lot about accuracy. Okay. However, recently we haven't yet discussed extensively the accuracy for the FMCW and the bit width of FMCW we need to have. Anyone wants to give me an example on how much accuracy we need here? Or how would you go about calculating accuracy?
Well, I think it kind of depends what signal we're trying to extract at what point in the process. Like the example we've come to before is extracting phase from the range FFT as a measure of distance.
Yep. So,
and so then
if we start from 1 millimeter as to measure 1 millimeter, right? Okay. How do we go about this analysis? Come on, folks. Let's see some creativity here. So I think what Dylan just said, right? Or was it Eric? I get confused between your voices. Sorry. Okay, so in any case, right? You go from D to phase, okay, right? Phase goes back to, what does the phase should go back to, folks? Phase will get to you like roughly the accuracy in the phase you need, okay? And then you can essentially say how accurately I can measure amplitude or should measure amplitude, right? Okay, and then once you know how accurately you need to measure amplitude, to make sure to get phase accurately, right? Remember, the ADC bit widths, right, okay, are done by sampling this point here, okay, right? So let's say your max amplitude here versus min amplitude, right, okay? You sample it, right, okay? And after that, you essentially take an FFT of it, right? And let's say if you have an IQ, it's fine. I think this probably goes a little bit outside the scope of so far our discussion, right? But you can go back from phase amplitude and then go back to the FFT analysis and you can kind of come up with the specification for the bit width or bit depth. It's called depth more than width, okay? Or more simpler trick to do is following, okay? You can take the maximum to the minimum signal, okay, right? And try to see how much variation they have, right? In terms of the signal quality, okay? So for example, right? D naught here, right? By the way, okay? It's smallest D naught at which I want to measure breathing and heart rate. The problem with the smallest D naught is that it will reflect a lot of signal back, okay, right? And then at this point, when you have a lot of signal reflected back, right, your breathing and heart rates variation becomes insignificant in amplitude domain, okay, or the phase you're trying to measure, right? And then essentially you can take max and min there to identify, okay, this is the resolution I need in the amplitude, okay, right? And that way you can also go about this analysis, okay? Again, these are advanced topics. These are not partly for the midterm just because I want to complete the story here. I gave you this intuition, right? Don't worry about the accuracy part. We are not going to ask about accuracy in the midterm, okay? Any other questions, any other topic you want me to cover? We can spend 5 more minutes on the actual class because we got delayed with the setup, right? Questions?
Yeah, well, I'm thinking about the two-tone and multi-tone setup.
Right.
So I think the issue is on the multi-tone setup. So basically, what we are so typically when we are talking about the frequency samples, the total bandwidth it should be n+1 times the frequency difference.
Sure.
So
I agree.
typically,
That's-
the total bandwidth should be n+1 times
So-
the delta B.
You're correct. Okay, I think that's what I referred to when I was saying, right? I think technically we should call it n+1, right? Okay, and that's what I kind of alluded to when Keshav was saying, right? So, okay, but that doesn't still explains the resolution, right?
But this means that if you have two tone, the frequency difference, you call it as B, but in fact the total bandwidth it should be 2 times B.
Got it. That actually resolves everything. That makes sense, actually. Yeah. Yeah, I think let me just clarify to everyone in the class, okay, what you're just saying, right? I think, yes, what I alluded to completes the actual story as well, okay? So I said the half of it, other half I think Renji just completed, okay, and clarified the mystery actually. Let me explain quickly. In this particular case, folks, okay, so here, right?
Professor, I don't think your screen is changing.
Oh, sorry. Thank you for reminding. Yeah. Screen stops way too often. So actually Renji made a very good point and it clarifies the entire mystery of it. Okay. This is all business about n of n and n plus one. Okay. All right. So let me just explain what he just made, right? So remember there are n+1 points here instead of actually n points. Okay. Well, technically, and the total bandwidth span, rather, let me put it this way. With this, the total bandwidth is spanned is n+1 times b. Okay. So when you have two tone, right, assume that this n is 1. Okay. So I think now I have a unifying way of explaining this. Okay. Right. As I was referring to earlier on as well here, right? If you remember, right, today we just discussed, right? These technically, when we say the separation is b over n, right? In totality, we may have n+1 points here technically. Okay. And therefore, what we tend to have is essentially this n+1 points gives you the bandwidth, or rather, this part then essentially is like, yeah, you can unify everything. Actually, the best way to solve, I like this way, okay, is assume we have n+1 points in frequency and they are occupying bandwidth b, okay, in frequency domain, okay. That's the unifying way of it, okay. Let me walk through it with a maybe add an additional page here instead of going through the same thing, okay. Okay, so what I'm going to assume is following, okay. I have lambda1 to lambda n+1, right, okay. These are separated by n over b, okay, right. So in total, still the bandwidth is b, okay, right. So the resolution therefore should be 1 over b, right, okay. Wait, this doesn't solve it, Renji, actually.
In this case, isn't it n?
Can I share my screen here?
Sure, go for it. Yeah,
I can. I can't share the screen.
you can. I can enable that actually. It's already enabled. Try now.
Okay. I can do it now. So, I'm thinking it in this way. So, basically, what we are having here is that we have this n points. So this is from 1 to n. And the total bandwidth, it should be looking in this way.
Okay.
So
that way you
starting
want to
from
call it
here
N
to
one
here,
times.
this should be n plus 1 times the delta b. So
Okay.
I call this distance as delta b.
That's fine. I think, yeah, once you do this, then it makes sense. Okay. I think, yeah, this is a better way to maybe unify both of them. Okay. So let me set everyone context for everyone a little bit. I got the part actually. Okay. So maybe let me start sharing again. Thank you, Renji. I think that's a good point. Okay. So what I think that's a good way to unify both of these analysis. Okay. I like it. So, by the way, guys, this may unify some things for you, but still follow, as I said, right? Follow, start from basics. Whenever I tell you two-tone, starts deriving everything from basic for the exam, okay? So what Renji is explaining is very interesting, actually, okay? Let's say our separation is, let's say, delta B, right? Okay. And you assign basically each tone with this essentially a cloud of delta B on each of them, right? So in total, your bandwidth becomes, in that case, n plus 1 times B, okay? Right? Okay, and therefore, right, or delta B rather, okay, right, and therefore the resolution, right, in this case is essentially, what is the resolution, folks? Come on, 1 over n plus 1 into delta B,
Delta
okay?
B.
This is your resolution, right? What is range? Come on, folks, range 1 over delta B. Sorry, yeah, that's correct, right? Yeah, that is correct. Does that sits really well with actually everything, okay? If you want to follow it this way, but again, just follow that simple two-tone analysis, okay? Does it, Helena, are you following this? So now let me explain, right? So when n is equal to 1, okay, which is essentially case of two-tone here, okay, right? In that case, resolution is 1 over 2b, okay, because this is the resolution, right? Okay, and range in that case is still 1 over b, okay, right? This actually is very nice unifying way of looking at this problem. I like it. Okay. Actually, it kind of works. I think I can see even for 3 and 4, I did myself the analysis. It does turn out to be what I am just saying, right? This actually works better. Keshav, does it make sense?
Professor, so in your lambda 1 to lambda n, you now have more points which you don't actually consider, right? Because you have a window for delta B.
I do consider that, right? Here. So look at this, right? I'm now considering this entire window with additional at lambda n with total of n plus 1 times delta B, right?
No. I mean for the signals that we're sending, right?
For which case are you talking about now?
So when we're transmitting,
Or are you
no,
talking about FMCW?
I'm just talking about the signal transmission that we do, right? So the whole reason we were doing this was because you have discrete signals that you're transmitting, right? Lambda 1 through lambda n, or in this case, lambda n plus 1. But because your bandwidth or your delta B has like a window to it, so that means you have now your starting tone is at lambda 1 minus delta B over 2. And your final tone is lambda n plus 1 plus delta B over 2.
Right. So,
but we're not considering those signals being transmitted in our system, right?
look, I think this is, as I said, it's an engineering approximation to get a unifying theory, by the way. Okay. This is not actually how like the thing is happening, right? Okay. So what Renji is giving is a unifying way of thinking everything. Okay. Technically, what I am showing you, right, for two-tone is perfect and exactly the way it is supposed to be. Okay. In a name of generalization, I just make it n times b and all those analysis still hold. Okay. Right. by doing this, right? Okay. What you can do is you can have one formula which can work for two-tone and even generalized case. Okay. That's the only distinction here. Okay. And by the way, right, as you said, right, because my frequency is a lambda 1 and lambda n plus 1 times delta b by 2, that essentially is captured therefore in this n plus 1 times delta b, correct? Right?
Yeah, it gets captured in the range and resolution. I was just thinking about the actual transmission and receiving.
No, so actual transmission still remains the way it is, okay? It didn't change, right? It was just a good unifying way to like cover this theory better with the overall math, okay? So you can skip this altogether, do independent two-tone analysis, three-tone analysis, four-tone, right? But if we say N, capital N, then do this capital N analysis, what we have been covering so far in the class, okay? This is a good way to unify, but not a good intuitive way to understand why this is working, okay? This is just like, look, I think when N is small, what two-tone does holds. And when N is large, what I'm doing holds, okay? Does that make sense? Keshav?
I think so.
If it confuses, drop this entire n plus 1 business, guys, okay? Just remember that for two-tone, there is a different formulas or not formulas. There are no formulas, by the way, in our class, okay? For two-tone, the analysis goes differently. For n-tone, the analysis goes differently, okay? Clear, Keshav?
Yeah.
Dylan, Eric, how are we doing? Puneet?
Yeah, I'm following.
Helena?
So one thing you could add to these equations is just that capital B is equal to n times delta B.
Sure, I can do that. All right, any more questions, folks?
I did have a question about
Go ahead.
how you determine the frequency for the high pass filter for the FMCW architecture.
Right. As in, like, it's more empirical, but yes, go ahead. So what you do is you measure like the delay in the transceiver itself, right? Okay, right? And like you make it up first, right? And see how much delay you're getting. And based on that, you essentially calculate and then design that beta, right? Is that what you're looking for? Or like, that's the question. Does that answer your question?
Yeah, I think so. So it's empirical, and you're looking to see where your interference is
Yes.
mostly located.
Or at what delay your interference arises, right? Okay, it's more of an empirical than a physical study. But you can, for example, say that anything, yeah, it's more empirical actually. Yeah, because a lot of components in your chain, right? Okay, in transmit chain can have good amount of delays which you didn't account for typically. Okay, so just saying that I would destroy or I wouldn't consider any components which are reflected within 5 to 10 centimeters so that I can get more dynamic range, right? Probably good, but not like perfect, because there is a lot of delay which gets in the transceiver added because you added power amplifiers, low noise amplifier, receivers, and bunch of architectures here and there, right? Each of them ADCs and whatnot, right? Or not ADC rather, but all those other things can cause reflections. Okay.
I have another question here. So, I'm thinking about what is the benefit comparing for the FMCW comparing to a normal OFDM modulation?
It's the interference cancellation. Okay. In the OFDM, the interference cancellation requires you to match the entire wide band. It's like the full duplex versus single high pass filter. Okay. So in the case of multi-tone OFDM, right, you will transmit multi-tone OFDM, right? And the reflection will also consist of multi-tone OFDM, and you have to reconstruct those small delays accurately and essentially create a full duplex radio there. Okay. Right. Okay. Versus in FMCW, this full duplex radio is simply done by having this simple small high pass filter. Okay, does that make sense?
Yeah.
So I think that sort of ties into my earlier question, right? Where we were talking about transmitting all n signals at the same time and receiving all n signals at the same time. But we would have a massive issue with the interference. And then so segmenting that out would be a huge problem. And that's sort of why we moved into FMCW, right? Because it has the advantages of transmitting many signals at the same time, but also cuts out the issues where you have the larger individual signals being sent out.
That's perfect. Yeah, that's exactly the thing. Yeah.
I see.